Very good morning. Last time we have seen a very important property. It is known as Archimedean property, and it actually is an application of supremum property of R, which we are assuming like an axiom for our further course as well. And then we also have an application of Archimedean property. Gives you this density theorem, means which tells you that between any two real numbers there are always an irrational numbers. Okay, so it will prove that if you look at means like kind of that dense, if you are aware about this meaning, what do you mean by dense subset is if the closure of Q. So if you have a set which is subset of R, we will say that it is dense in R if A bar is equals to R. So will you are you able to understand what do you mean by this A bar? A bar is the closure of the set A. Okay, which includes all interior points as well as all boundary points. And if you take any points, it is going to be a limit of certain sequence inside A. Okay, so so Q is a set of R, and you can actually establish that Q bar is equals to R, is close of Q. So you can take, so every Q means every element of Q bar is inside R, and every R is a limit of Q. Okay, so this includes all the possible limit points of Q. So you can take any real number. Okay, you can take any real number whose limit is going to be whose sequence you can define as a sequence of rational numbers, and which is going to converge to the number. So that we are going to maybe look later. Okay, when we define the concept sequences and then their convergence or divergence. Okay, right. So we are postponing this concept for some time. Okay, right. So here is the definition of sequence. So sequence is, if you noted previously, set could be finite or could be infinite. And we have seen that if you have the set is countable, you can always enumerate it, okay, in certain order. Okay, and one of the other notion which we have forgotten to mention here, the order property of R. So you take any two real numbers, A comma B belongs to R. There are only two possibilities, either either three possibilities: A less than B, or A equals to B, or A is greater than B. So you can define, so you can always compare this, and this is derived directly from the notion of positivity. So not trichotomy, but it's a kind of consequence of or corollary of that part. Okay, so so you can always put them all in the order. So you have also seen that set of natural number, when you are trying to write it, it is always 1, 2, 3, 4, 5, 6, and so on. Put them in order. Okay, and if you want to associate a function, okay, so which set is a sequence of real numbers is a function defined on the set n of natural numbers whose range is contained in the set of real numbers. So we are talking about sequence of real numbers. So then in the later on stage, you can generalize this as a sequence of complex numbers, or a sequence in some spaces, okay, 2-dimensional space, 4-dimensional space, and so on, that you will see later on, maybe in linear algebra course and so on. So what it says is it's a function. So we denote it by, let's say, x, whose domain is going to be set of natural numbers and whose range is inside the set of real numbers. Okay, so this is a function defined on the set n of natural number whose range is contained in the set of real numbers. It may or may not be bijection. Okay, from n to r. Okay, so it may be uncountable or it may be countable. Okay, right. So because it depends on the range. Okay, right. Now, so how will we define is x of I? If I define x of I is equals to I. Okay, so and more mathematically, how will we symbolize these sequences as with suffixes xi, x suffix with I. So here I is belonging to natural number. So you can unique number here x1, x2, x3, x4. So you have put it down already in order. So but it may or may not be in order. So you don't you first put the means like odd numbers or even numbers like this, or you can decide first prime numbers and then not prime numbers and so on. Okay, so you are associating a function on this. So by defining this, so this is a very, so the set of natural numbers you can assign a sequence. So it is enumerated. We have already seen they are enumerated x1, x2, x3, x4, x5, x6 means in putting them in order of this notation. So a sequence of real numbers is a function defined on the set n of natural numbers. So this whose domain is n. Once set that domain is n, it is defined for every value of the domain, every point in the domain. Okay, and this range is contained in the set R of real numbers. Later on, you will generalize to some space. Okay, so that we are going to take it later, maybe not in this course, maybe if we come go for another course, then we are going to see that. Okay, so this is sequence is nothing but a function. Okay, and here see here one more thing I would like to mention. Sequence is something different from the like set. Okay, so you can have like x from n to r. I can define another sequence x of I is equals to fix, let's say 1. Okay, so it's a constant sequence. You say that this is 1, 1, 1, 1, and so on. And most of the time it's like or you have this is xn. So xi is equals to 1 for all I. So the notations, you will find different notations here. Okay, so this is a sequence, constant sequence. This is not a set. When you want to write a set, it's a singleton one only. Okay, so in the sequence, the terms may be repeated, may not be repeated. Okay, right. Okay. Now, so you can now define any sequence, right? You can choose, let's say, a number. Let's say, so let you have another example of sequence. Let some A belongs to R. Okay, and you can define x of I is equals to a to the power I. That also is a sequence. Later on, we will see whether this will converge or diverge. Okay, so I belongs to natural number, and so on. Okay, right. So we are going to look at now whether convergence or divergence, how it will define. Okay, right. So the constant sequence is we are going to write in the braces, open braces instead of curly bracket, because curly brackets are, we are going to use it for set. Okay, right. Now if B in R, so we already defined this. So instead of I, you can use here N. Okay, so the sequence of even natural numbers, that also define a sequence. Then the very famous sequence is Fibonacci sequence. So which you can write. So you can start with 1, 1. Then the third element is the sum of the previous two. So the next is 3, the next is 5, next is 8, and so on. So 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, and so on. So this is how the Fibonacci sequence defined. So whether, so this is means like this is in order increasing, but whether we can talk about whether all increasing sequence is convergent or decreasing sequence is divergent. So we will see these concepts as well. Okay, right.
Sir, so only difference between sequence and a function is that sequence has a domain of only natural numbers.
Yes, it is fixed that set of natural number is the domain.
Okay.
Okay. Right. Also, this is need to be clear that it may not be 1 to 1, it may not be on 2. Okay.
Sir,
Right. Huh.
sir, I can take a sequence of root 2 to 10 to root 2.
Yeah, you can.
So, but that
Inductive.
would not be a natural number. No?
Pardon?
If I take a b equal to root 2,
B equal to root 2, yes.
yes, then the sequence would not be a natural number.
No, B is any real number. Nah. What is here inductively is going on is power. In power, it is varying, right? 1, 2, 3, 4, 5.
Yeah.
B is fixed. So we don't mind whether the squared term will be natural number or cubed term is going to be natural number. We don't mind that because our range is in R.
Okay, sir. Okay.
Okay, so the outcome should be a real number. That we say
Yes.
that it's a real valued sequence. Okay, or some other, if you look at function also, it's a real valued function. You can say.
Sir,
Okay.
On the set of natural number. Yeah.
sir, uh, the range of that function contains all real number or some real number.
A subset of real numbers. So range of x. So range of x is going to be a subset of real number. It may be full, it may not be full, but it is not possible that it's going to be complete R because otherwise it's going to be onto. But if it is a 1 to 1, if it is also 1 to 1, it is not be possible 1 to 1. Otherwise, what will happen is R becomes countable, and but we know that R is uncountable set. Okay, right. Okay, so now let's talk about the limit of sequence. So once you define a sequence like x1, x2, x3 in some order or may not be in order, but where does this converge to in the limiting sense? At the last value of n, what is the value? Okay, that you wish to determine. Now, if you go back and check the constant sequence like B, 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 and so on, and you know the what is the nth element, when at any place it is going to be B only. So you know the limit is going to be B only. Okay, but if you instead of B, you are going to take their powers B square, B cube, and so on. Then you can then you can define the cases like B is greater than 0. Let's first assume that B is greater than 0. Now, if suppose B is greater than 1 also. B is greater than 1. What will happen if B is greater than 1? And you note that if A is less than B, 0 less than A, and n belongs to natural number, A to the power n is less than B to the power n. Okay. Now, what will happen is if B greater than 1, so once you take the square, B square, it's going to be more, means it's going to be large than B, and then B cube is going to be more. So it's going to be B less than B square less than B cube and so on. And once B is greater than 1, it's going to be huge, very huge number. You can say suppose even you talk about 2 to the power 1000. Suppose B is 2. Or to the power, you can say 1 lakh. Because 1 lakh is also a natural number. So it's not, so you can't say how much use it is, you don't know. So this is an example of, it's going to be divergent. But instead of this, if you take B between 0 and 1, suppose 0 less than B less than 1. So once you increase the power, it is going to be reduced. but it is not go below 0, right? And it's going to be towards 0. So what is the intuition here is, when you take any b between 0 to 1, it's going to be tending towards 0, because n goes large and it is going smaller and smaller and smaller and going towards 0. It will never cross to 0 on the left side. Okay, so these are the intuitions with these some standard sequences. So how will we identify, means how will we define the general notion of it? Okay, so I want to explain what the meaning of this definition. What it says is x equals to xn in R is said to converge to x in R, or x is said to be limit of xn. So if for epsilon there exists so and so. Okay, what it says. So if I want to elaborate the definition, we have been given with a sequence which we are going to denote it by like this. Sometime you will see. So this is abused notation, you can say n equals to 1 to infinity. This is also one more notation. So we are not bothering about what type of notation. We know that this is a sequence. Okay, means x is a real valued function defined on set of natural numbers. So we say that this limit of xn is equals to x. Okay, so the question is whether it exists or not. Okay, then if suppose it is exist, when you will say this is xn going to be closer to x1. So what is so how will you look at here like x1, x2, x3 and so on. So if you have this sequence enumerated, and if you are saying that in limiting value it is going to x, so if you look at here, so let's say this point is x, and you take any neighborhood of x. So this is, let's say, x minus epsilon and x plus epsilon. You take any neighborhood. So when you will say this limit is going to be inside x is whenever after the only means except the finitely many terms. Suppose except is like say, suppose xn. Except these finitely many terms, xn plus 1, xn plus 2, and so on. The rest of the terms are going to be live inside this neighborhood. You take any epsilon bigger than 0. So this is what the meaning here, that you say the limit is convergent. So except finitely many terms, it can be, means finitely many terms may sit here, may sit here, may sit here, may sit here. But except them, or means afterwards, you can say afterwards, these terms are going to be inside this, the neighborhood of x. So you take any epsilon is however small as possible. You can take very small, you can take very large as well. Okay, so this is how the definition is designed. So this then we take like, because large value of n is going to be very near to x, that's what it means, right? Okay, right. So this is what the definition it says. So now if I want to mathematically define it, this says that for every epsilon bigger than 0, there exists in natural numbers n. So n is matching with our set of natural numbers. So we are identifying one another notation k, which certainly depends on epsilon in natural number, such that mod of xn minus x is less than epsilon for all n greater than equals to k epsilon. So after k epsilon onwards, all are falling into this neighborhood infinitely many terms. We don't bother whether some of them are also coming or not inside. Okay, so only finitely many terms are allowed to be remain outside. Then you say that limit is going to be x. Okay, right. So with this definition, what can we tell about our defined sequences that we are going to see? So this is a mathematical definition in epsilon. Okay, right.
Sir, I do not understand what neighborhood about.
Neighborhood is a neighborhood of x. So if you recall, the definition of neighborhood is that v epsilon of x is equals to set of all real numbers such that mod of y minus x is less than epsilon.
Yes, that understand, but x1 and that. x1, x2, x10 lies between x minus epsilon and x plus epsilon.
Okay. No, see what it is saying, definition. I'm talking about definition. What it's saying is there exists a means like you can say a barrier or whatever. Say only finitely many terms are outside of the neighborhood of x. That's what it says. Okay, that's what only it allows. That means limiting sense. See when you are writing in some enumerated one, or you can say in order. So after sum, that it is going to be very closer to x only. That's what it means.
That xn very closer to x.
Yes, as n goes to infinity. Okay, so as n goes to infinity is capital N here. Okay, here is if you take n goes to infinity, or you can say this small n is going to infinity, means you are going towards large and large value. It is going closer to x. Okay, and it is sitting in very. So you say it may be n, maybe x lakhs is one. Means n value, capital N value may be million. Okay. After this n million, the other all the x is 1 lakh 1, 1 lakh 2. So those terms at this are going to be live in. You can see, or you can take however small as possible. There is no restriction because here saying that for every epsilon bigger than 0, so can be taken as small as possible. You can take as big, but that will not help. Only you have to vary that epsilon. Okay, so now things will be more clear by looking at the problem. Okay, right. Okay, so some of the comments here, observations. If a sequence has a limit, okay, suppose somehow you are able to verify that the definition is there. So if a sequence has a limit, we say that the sequence is convergent. If it does not have limit, we say that the sequence is divergent. So that we are going to look at some examples. Second, when a sequence has limit, we will use the notation. The following notation we are going to use: limit of xn equals to x. Okay, sometime you will also see the following notation, that limit n tends to infinity, xn is equals to x. That also you will see some notations. So there are separate different notations with respect to different textbooks. Okay, so we not worry about this. We will worry about the concept here. Okay, right. So let's okay, one more observation is a sequence in R can have at most one limit. So if the limit exists, it is unique. So this is going to be uniqueness. This tells you about uniqueness. Okay, so that we are going to establish now. So uniqueness we are going to establish, and then we will see the examples. Okay, right. So here, so let x comma y belongs to R be such that limit of xn is equals to x, and also let's say limit of xn is also y. Then our claim is x equals to y. Right? Okay. Now since, so let epsilon bigger than 0, then since limit xn equals to x, so this k epsilon, which certainly okay belongs to n, such that mod of xn minus x is less than epsilon for all n greater than equals to k epsilon. So that is due to the definition of convergence of the limit. Okay, and also there exists, let's say what is another denotation we are going to use. Let's say k star epsilon belongs to natural number such that mod of xn minus y is going to be less than epsilon for all n greater than equals to k epsilon star. Now let's say k is equals to maximum of k epsilon and k epsilon star. Okay, then we are going to now we know that 0 less than equals to mod x minus y, which is going to be, so we are going to add and subtract minus xk plus xk and minus y. Now use the triangle inequality, less than equals to mod x minus xk plus mod of xk minus y. Now since see k is maximum of this, so k is greater than equals to k epsilon as well as k is greater than equals to k epsilon star. So this will satisfy both the inequality. So I can instead of epsilon, I'm just modifying this epsilon by 2. There's no worry about it. You can still keep the epsilon here. So this is going to be less than epsilon by 2 plus epsilon by 2, that is epsilon. So you have started with epsilon bigger than 0 and you are ended with 0 less than equals to mod x minus v less than epsilon. So this is how you can, again, you take any epsilon, this is still true. So this is what it gives you, is this implies for epsilon or for every epsilon bigger than 0, since epsilon is arbitrarily chosen. Okay, that is arbitrarily chosen. So you can still arbitrarily chosen. So implies for every epsilon bigger than 0, 0 less than equals to mod x minus y less than epsilon. So this is true for every epsilon. This is true if and only if mod x minus y is 0. And that is true if and only if x equals to 1. That we have already seen one result. Okay, that it says that 0 less than equals to a less than epsilon for every epsilon bigger than 0, then a is equals to 0. We are using this result here. So here a is mod x minus y, and you know that mod x minus y is equals to 0 when x equals to y. There is no other possibility. So this establishes the uniqueness of limit. Whenever it exists, it is unique. So a sequence cannot have more than one limit. That's what it means. Okay, right. Now let me have those examples now. Let's say some example. So if you have the sequence, let's say xn equals to 1 for all n. So what will be, so let epsilon bigger than 0. What will be the limit? So let limit will be what it will be, because it's a constant sequence. So what it so you have to guess. Okay, so we are going to show that claim is limit of xn is equals to 1. Okay, right. Now let epsilon is bigger than 0. Now mod of xn minus x. So what is x here is, this is x. So this is equals to mod of xn minus 1. But you know that for every n, xn is 1. So this is equals to 0. And which is less than epsilon for all n. So this certainly says, this claim, this proves our claim. Right? This is because for every n, it is like, so mod xn minus x is going to be less than epsilon for every n. So it's going to be establish our claim that the limit of xn is equals to 1. See, mod of xn minus x, you need to show that what you need to prove. Mod of xn minus x is less than epsilon for all n greater than equals to some k epsilon. But here is k epsilon you can take for all n greater than equals to 1. K epsilon is you can take 1 itself. This follows the definition. Because xn is 1 for every n. So 1 minus 1 is what? 0. And your limit value is also 1. Okay, that you have to guess actually. Intuition will tell you. So here is xn equals to 1 means it is only sitting here only. It is not going anywhere. So you take any neighborhood, all the members are sitting here only.
Sir, I get this, but I don't know why in the definition is it happening so that xn minus x is always less than epsilon. Means I didn't get that point.
For this problem or
No, not for this, for the definition. I means just we have to remember the definition, or is that we have to understand something in that? Because I can't get why it is happening.
Okay, so see, what do you what do you observe from the definition? If I go back and let it be the definition here. So let me here. Okay, so what it says is you take epsilon however large or however small as possible. Okay, you will always able to identify. So this, if I read this, you will always able to identify a stage. You can say this is a stage. Okay, so afterwards, all the elements are going to be lies in the neighborhood of x. Okay, so that is, we are going to read it like this. Now, if you take epsilon very small, what it tells you that it's very means after some like n means like stage like 1 lakh, you can say x1 to x3 and so on x lakhs. So x lakh 1 onwards, all the other entries are going to be sitting closer to x. So this is how you will see that limit of like, see, if you want to find a certain point in the some city, what you will look for? You will look for the very closer one, the next one next to it. Okay. So, but if it is not able to, you are not able to find out, then you will look in the area. Okay. So that area means many peoples will be remaining afterwards. So if you are going in the single direction, you can see. And see, because it's a set of real number, you cannot go any direction. It's like you say, I will follow the parabola path, I will follow the cubic path, or and so on. It is not possible. You are talking about real line, either on the left side or on the right side. Okay, there's only single path on the set of real numbers. When you talk about complex numbers, two planes, is two-dimensional plane, the situation will be different. Okay. So here you can only follow, it's like you can locate him and then you go in the single direction. So after some, like suppose lakhs shop, okay, afterwards every shop is going to be nearer to him only. Means like you take any epsilon greater than 0. This is how I can say is closer. You can say the closer point you are trying to identify. Okay, this can be seen as an example with what I can fit it here right now. Okay, so epsilon, see, this all depends on epsilon. If you take epsilon, however, as small as possible, what does this imply? Means after this is a barrier here, greater than equals to k epsilon. So k epsilon, we don't know whether it's a 10 lakh or a 1 lakh or 100 or 10. We don't know. So you are able to identify that such barrier. It's like k epsilon is a number, natural number, which is you can identify. Afterwards, all the other terms are going to be very closer to x if you are taking epsilon as small as possible. That's how this definition is.
Okay.
Okay, right. Okay. Now, so we have seen one example here. Now, another example, xn is equals to b to the power n and belongs to natural number, and you have b is greater than 0, and let's say for safe side, let's say 0 to 1. So what we can show is, I want to claim is, because I know that whenever b is less than 1, as you increase the power, it is going closer towards 0. Okay, so that you will certainly get from here that limit of xn is equals to 0. We want to first identify that thing. So now this is equals to x. Now what I want to show is let epsilon bigger than 0. I have to start with. Okay, so this is definition. Later on you will find some test will be there. Okay, so test will be easier than the following the epsilon, so that we are going to look at later on. But let's see how the test is applicable. So let epsilon bigger than 0. Now mod of xn minus x is equals to what? Mod of bn minus 0. That is equals to mod of bn, which you can apply the absolute number function property, that is going to be mod b to the power n. Now since b is greater than 0, you can write it as b to the power n. It's in natural number. What do you want here? You want is less than epsilon. So can you solve this inequality now? See, ln function is increasing, right? So if you look at the function ln of x, natural, so the derivative is 1 by x. Whenever x is greater than 0, this function is increasing function. So you can apply, this implies, so ln of b to the power n is less than ln of epsilon. So this will imply I will apply, this is true if and only if this happens. This is true, so you have n time ln of b is going to be less than ln of epsilon. Right? So what it tells you is, now this is if and only if n is greater than ln of epsilon divided by ln of b. Why suddenly I have changed this greater than here? If you are able to get it. Because see, ln b I have divided.
Because
So b is less
Because
than
negative.
1.
B
base
is
and number
less
are
than 1, so
opposite.
ln b is a negative. Okay. So what you can design is now this nearest integer to next of it, that you can design as k epsilon. Okay, so for any n greater than this, the next integer of this is like +1, you can take as well. Okay, so that very next integer onwards, this you can go now reverse direction. So now from here you can go this direction, and this all these things will be remain true when you start with an epsilon. So you are able to identify a natural number k epsilon such that this mod xn minus x is less than epsilon. So my claim is proven now. Okay, but every time it is not possible. So certainly you require some method or test or something, okay, which will identify that, okay, without epsilon can we identify the convergence or divergence of the sequence or not. Okay, so we are going to look at some divergence sequence as well. Okay, let's. Okay, right. Now, so this next is a very this result. It looks like here is a very long result, but it's, in other words, they are equivalent definitions of the convergence of the sequence. So if you read that x equals to xn be a sequence of real numbers, okay, and then let x in R, the following statements are equivalent. X converges to x, so you this also one of the notation. X equals to x, and then we say that x converges to x. So this is also follow the definition. For every epsilon bigger than 0, there exists a natural number k such that, means after this kth stays, the terms xn sitting closer to x. That's a definition. The second, so now if you open up this bracket, mod xn minus x is less than epsilon. So you know that mod of x is less than equals to c, or less than c, if and only if minus c less than x less than c. So this is going to be using this one. Okay, the third thing is it's replacing the definition in terms of neighborhood. So this is what is this is mod of xn minus x is less than epsilon, means xn belongs to epsilon neighborhood of x. This after some stage. So these all are the equivalent definitions of the convergence of sequences. Okay, so these are equivalent so that you can verify that you're on. So this, you just follow the definition of what is v epsilon of x, And as I have told you, for this, you just open this here and you will get this. Okay, and this is your definition only. Okay, right. Now, these are the examples. So, out of which we have only tried with the fifth one. Okay, so you can try with the first one. So, I can try with the first one. So this is, so x is, here is 0. So, let epsilon bigger than 0 be given. It's a very simple be given. So, for this epsilon, are you able to identify the space? So, now, mod of xn minus x, what it is mod of 1 by n minus 0, that is equals to 1 by mod n, but n is natural number and it is positive. What you wish to do, this is going to be, I wish this is less than epsilon if and only if n is greater than 1 by epsilon. So your k epsilon, I choose k epsilon is, you can choose k epsilon is greatest integer function, and so next to this number also you can choose, but this will also work. Okay, so for this problem, the result is good. Now the second problem, if I go with the limit 1 by n square plus 1 is equals to 0 is equals to x. So again, I will start with let epsilon bigger than 0. Now you have this mod of xn minus x is equals to mod of 1 by n square plus 1. This is going to be 1 by n square plus 1 less than epsilon. This is if and only if n square plus 1 is, you have, this is greater than 1 by epsilon. Okay, so this is if and only if n square is greater than 1 by epsilon minus 1. Now there are two possibilities. 1 by epsilon is less than 1 or 1 by epsilon is greater than 1 or equals to 1. Okay, so there are three cases. So you have one case is 0, one case is 0 less than epsilon less than equals to 1, and another case is epsilon greater than 1. So in the case 0 less than epsilon less than equals to 1, this is less than 0. So any n, so for this case, if I refer this case, this is if and only if n belongs to natural number or greater than equals to 1. Because this is negative and you know that square is always greater than 0. So for any n, it will be true. Now for the second case, what will happen is 1 by epsilon. For the case, okay, epsilon greater than 1, it is going to be 1 by epsilon is less than 1. So 1 by epsilon minus 1. So this is going to be true for this one. So this is if and only if. So here n is greater than equals to 1 is fine. For this case, what is there is 1 by epsilon greater than equals to 1 you can put here. It's not a problem because 1 minus 1 is 0, still it is true. Now for the case 0 less than epsilon less than 1, so 1 by epsilon is greater than 1, so 1 by epsilon minus 1 is greater than 0. So then you choose if and only if n is, so this is greater than 0 number, so n is greater than square root of 1 by epsilon minus 1, and then you take k epsilon as the nearest integer square root of 1 by epsilon minus 1 plus 1. So you see what you are doing here, you are artificially defining. So this is how the proof will go here. So you have to artificially create the k epsilon for a given epsilon so that this satisfies the definition of the convergence. Okay, right. Okay. Now these problems have done. So rest of the two, these are also follow the similar way. You have to also show in the same manner. Okay, or you will discuss in the, if you are not able to get it, you will discuss in the tutorial session. Okay, right.
Sure.
Yeah.
Why we had done this +1 in that k epsilon?
See, the greatest integer is what? I just don't want to get it out here. So greatest integer means like on the real line. Suppose this is a real number. Okay. So what is the greatest integer function is sitting on the nearest integer, right? So this side. Okay. So sometimes you people also use roof function or floor function. So that is why for the safe side, I'm just using here +1. So if this is this side, that is fine. If you're specifically using greatest integer function. Okay, if you are using floor function, you have to go the next +1. Okay? Okay, right.
Okay, sir.
This is why only for the safe point of view here. Okay, because whenever it is true for this, it is also true for, if it is true for this, because we have to find, it doesn't matter if you skip one step, one term, doesn't matter, because because you can skip finitely many terms, only finitely many terms. Infinitely many terms should lie in the neighborhood, right? This is our point.
Okay, sir.
Okay.
Sir, for
So-
second case, k epsilon not must be equal to 1 for n greater than 1.
Yeah, here is for this case, k epsilon is greater than 1. K epsilon is equals to 1 itself.
1, yeah, 1 itself. Okay, sir.
Okay, right.
So,
Now,
so,
yeah,
so in second case, epsilon naught is greater than or equals to 1, right?
where?
Epsilon is greater than or equal to 1, sir.
There
So,
are two
n
cases.
square 1 by epsilon is less than or equals to 1.
Pardon, n square?
N square, so then 1 by epsilon naught, 1 by epsilon will be less than or equals to 1 also.
Yeah, 1 by epsilon is less than equals to 1, yes. So 1 by epsilon minus 1 is less than equals to 0.
Yes, sir.
Huh.
Yes, sir.
Huh.
Then,
So,
if we took epsilon value greater than 1, then we'll get 1 by epsilon minus 1 as less than 0. So
negative number, yes.
then n square, but n square is always a positive number, right?
Yes. So any n value will work now. Because n is greater than equals to 1. And it is inequality always true for any n equals to 1, 2, 3, 4, 5, 6.
Okay, sir.
Did you get
Okay,
it?
sir. Yes, sir.
Right? Okay, because this obviously follows. Because this is less than, it is sitting on the left of 0 and it is sitting on the right of 0. So this for every n it follows.
Okay, sir.
Okay, so this is a very first comparison test, you can say. So what it says is let xn be a sequence of real numbers and let x in R if an is a sequence of positive real numbers with limit an equals to 0. And if for some c and some n, we have the following criteria. Then you can show that limit of xn is x. So what it says is it is going to be bounding, you can say. It's bounding by some nth term, which is going to be positive because this mod is there, right, sitting. So it cannot be negative. C is greater than 0. So an also has to be greater than 0 to satisfy this condition. Okay. So how will you use it? So let's here is this problem. So if you are, I'm going to use this, I know by n plus a minus 0. It's a very simplest example, that is equals to 1 by n plus a. So that's equals to 1 by n plus a. Since a is greater than 0 and n is also greater than equals to 1. It's certainly less than 1 by n. Right, and you know that limit of 1 by n is equals to 0. So therefore, limit of 1 by n plus a is equals to 0. So only need to show now is limit of 1 by n is 0. Very basic result what we have seen. So this is how I can use this for this simple example. Okay, so not only this, I can go back and I can also do use this criteria for the problem what we have done for this limit of 1 by n square plus 1 is equals to 0. I know that 1 by n square plus 1 is going to be less than 1 by n square. Okay, and which is less than 1 by n. And limit of 1 by n is 0. So this is going to be okay. So here, so this is in the shape of mod of xn minus x less than c time an. So if you compare, what is an is 1 by n. What is c is 1. What is xn is 1 by n square plus 1. What is x is 0. You compare all the things. So only need to show that now is limit of 1 by n is 0. Okay. If you go back and check the fourth problem where we want to show that limit of square root of n plus 1 minus square root of n is equals to 0. Okay. Now, if so for solving this, to take this, so you have xn is this, x is this. Okay. Right. So now, I know xn minus x. I want to evaluate first this thing. This equals to square root of n plus 1 minus square root of n. Minus 0 is nothing to worry about it. So I will certainly rationalize this. So I will multiply and divide by this one. Plus root n. See, because of this minus sign, okay, because of this minus sign, you are not sure that this is going to be infinity, because you know infinity minus infinity is not defined. Okay, as n tends to infinity, this is also goes to infinity, this also goes to infinity. Okay, that we are going to look at also later on, that properly divergent sequences. Okay, but whenever it is plus here, you can certainly go for it. Okay, so minus here, so that will give you n plus 1 square. N plus 1 is a minus b into a plus b. If you apply, so what you will have is n plus 1 minus n divided by square root of n plus 1 plus square root of n. So that is equals to 1 by square root of n plus 1 plus square root of n. Now, this is going to be certainly, you know that square root of n plus 1 is greater than square root of n. So, so square root of n plus 1 plus root n is greater than 2 root n. So 1 by of this, if you take reciprocal, this is going to be less than 1 by 2 root n. So how then this will imply, so I am just using this. So this will implies mod of xn minus x is less than equals to less than 1 by 2 root n. Now c is equal to 1 by 2, an is equals to 1 by root n. So now you need to show that limit of an is 0. Then you can certainly prove that limit of xn is x. So this is how you will use this criteria for proving, establishing the results. Okay, so only need to prove is limit of an is 0. So how will you prove? In the same manner what you have done for 1 by n. Okay, right. So this is one criteria. Another here is, okay, so like we have seen the set, when you will say set is bounded. Okay, so that's when you say the set is bounded, if it has an upper bound and it also has a lower bound. Okay, whenever it has upper bound as well as lower bound, then you will say that the set is bounded. So, but the sequence contains infinitely many elements. They may be repeated, okay, but they are infinitely many. Okay, so when we will be able to say that a sequence is bounded, so whenever it lies inside a closed interval minus m to n, you can say, or open interval, that's also fine. Okay, so a sequence x of real numbers is said to be bounded if you are able to identify a real number m such that mod xn less than equals to m for all n in n. So means you have the sequence x1, x2, xn and so on, but you are able to identify a closed interval where it will be like open disk or closed disk. I mean, sometimes this I should not use here because the complex is not, it's a 2 dimension, it's a 1 dimension, it's a closed interval. Okay, right. So see, what will be the bound is, if the sequence converges, the bound is nothing but the, okay, that you will find out by the definition. Okay, right. So what is the first observation is a convergent sequence of real number is bounded. Okay, so what it says is, if you have sequence and if it is convergent, then it is necessarily bounded. Okay, so how do you use this? Okay, you can use this to prove that the sequence diverges by proving that it is not bounded. Okay, so if you prove that a sequence is not bounded, it's certainly not convergent. Like differentiability implies continuity, but continuity may or may not imply the differentiability. So this is a necessary condition. So how will you establish this result? It's very simple. Okay, it's very simple. So that you can certainly prove. So let you have xn be a sequence, and a limit of xn is x. So convergent and its limit is x. And we claim that xn is bounded. So how would you show this? Now, limit xn is x. So let epsilon bigger than 0 be fixed. I fix this epsilon. Okay, but for this epsilon, you will able to identify a k epsilon such that mod of xn minus x is less than equals to epsilon for all n greater than equals to k epsilon. Okay, right. Now what you will choose? So I will choose m is equals to maximum of, see epsilon greater than 0 we fix real number. So all the after k epsilon stays, k epsilon and k epsilon stays, all thus sitting in the neighborhood of x. This with length of in the interval less than equals to epsilon. So what I will choose is m is the maximum of x1, x2, and so on xk epsilon minus 1, and this this is going to be mod x plus epsilon. I will choose this. Why this mod x plus epsilon is because when you look at mod of xn, so I will subtract and I will subtract x and adds x, which is certainly using triangle inequality less than equals to mod of xn minus x plus mod x, which is, this is going to be so mod xn. So from here for all n greater than equals to k epsilon, so this is for all n. So this is going to be less than equals to mod x plus epsilon for all n greater than equals to k epsilon. So if I use this equation here, okay, now if you choose m equals to maximum of this mod x1, mod x2, and so on, mod of x k epsilon minus 1. If I use this, then it certainly says to me that mod xn is less than equals to m for all n greater than equals to 1. So till this n greater than equals to k epsilon, it is bounded by mod x plus epsilon, and after before k epsilon, you have taken all the magnitude value and take the maximum over it, that will define the n. So which says that xn is bounded. So if you have a convergent sequence, it is necessarily bounded. Okay, but then you can show that if a sequence is not bounded, that certainly implies that the sequence does not converge. Okay, right. So we are going to use this by an example. So let's consider one example here now. So let's see the sequence xn is equals to, you can say, n. Okay, so this sequence is not bounded. Can I prove this? So we can show that claim is xn is not bounded. Suppose it is bounded, what will happen? So on the contradiction, suppose there exists an m greater than 0 such that mod of xn is less than equals to n for all n greater than equals to 1. So this certainly implies n is less than equals to m for all n greater than equals to 1. But which is not possible, because you can see, you can again use the how do we have proved the Archimedean property? That by using the fact that set of natural number is unbounded. Okay, so you can use that similar result here to show that that well ordering. So you can this will says that set of natural number is has an upper bound. Okay, it has an upper bound and it is a non-empty set. So completeness property implies that supremum of n is some u. Okay, and then you can, then u minus 1 is not an upper bound. So you will always able to identify some n such that u minus 1 is less than equals to k for some k. So but then u is less than equals to k plus 1. So k plus 1 is a natural number which is sitting on the left, on the right of it. So u is no more upper bound. So by using such a contradiction, similar contradiction what we have used in during proving the Archimedean property, okay, that you can establish that this cannot hold true. Okay, so our assumption was wrong. There does not exist any such m, so xn is not bounded, so this sequence does not converge. Okay, right. Now let's see how the algebra of sequence is. If you perform the sum of two sequences, how will you perform it? Very first question is, how will you write the sum of two sequences? How will you write the product of two sequences? How will you write the division of two sequences? Okay, those things are also question. But like you have done for the functions, similarly you are going to define the sum of two functions, some difference of two functions, and so on. Similarly, you will define the for the sequence as well. So here is that. So let x is xn and y is yn be sequences of real numbers, and you have assumed that that converges to x and y. So I'm going to define how this x plus y is defined as xn plus y. Okay, so if you have here minus, you will use minus. If you have here let's say dot, means multiplication, you will use your dot. Okay, so similarly c times x you are going to define as c times xn, the sequence like. Okay, now another is x by y. Now this can be defined by xn by yn, provided what should be there, that denominator should not vanish. Means y is a sequence whose each term, okay, is non-zero. Okay, non-zero real numbers, yn should be non-zero. Sorry, yn is non-zero. The next thing is now then also sorry, and also that converges to a non-zero number. So of 1 by y or 1 by yn, you can say has to be non-zero number. Okay, then the quotient sequence converges to x. So similarly algebra follows for the limits as well. So x and y respectively, and let C is in R, then the sequence is x plus y, x minus y, x dot y, and cx. This is how they are defined, first two. Then they are converges to small x plus y, small x minus y, x into y, and cx respectively. So sum of the limits, difference of the limits, product of the limits. So whenever you do this, there is no problem. Similarly, scalar multiplication also not a problem. Only the problem is the quotient sequence. Okay, means where we are putting in the numerator and denominator sorry, sequences. Okay, right. So then if x equals to xn converges to x and z equals to zn, so z also you can take, because here we want to identify very special property that it should be a sequence of non-zero real numbers, and that converges to a non-zero set. Okay, it should not be 1 by n and 1 by n is tending to 0. So that will not help here. So then the quotient sequence x by z converges to x by z. Okay, so these results can be established very easily. So that these things you can look at in the tutorial part. Okay, so this algebra we are going to use for proving some of the results. Like now you can establish the results for like if I put here if I give you some examples, you can certainly use now. So let's say xn is equals to 2 by n. You know the limit of 1 by n is 0. Okay, so then limit of xn is also 0. 2 times limit of 1 by n, that is equals to 0. Second, let's say xn is equals to 1 by n plus 1 plus 1. Okay, then limit of xn is equals to, now note that in the previous result that you are first priorly assuming that both the sequence converges, then only it holds. Okay, if the sequence does not converge, you cannot use the algebra of the limit as well. For example, you can take xn is equals to n and yn is equals to n, and then you define xn minus yn 0. The limit is 0, but this does not converge, this does not converge. Okay, xn minus yn, they are equals, they are 0. Similarly, if you want to with plus, you can define with minus, so minus minus plus, so xn n minus xn plus yn you can check there. So you need to first priorly assure that individual sequence also converts, that only you can apply. Okay, so you will get the counter results as well, that some of the two sequence may converge, but the sequence itself, those are the individual sequence may or may not converge. That is possible, but it's only one way. Okay, so now since we know that this the first term is 1 by n plus 1, and we know that by comparison test you can take 1 by n plus 1 is less than 1 by n, and you can use that result previous, since limit by n is 0, so limit of 1 by n plus 1 is 0. Now second term is constant sequence 1 1 1 1 1 1. So this will be converges to 1. So this is going to be both sequences converge, so sum is converged to this sequence, just this limits. So that is equals to 0 plus 1, that is equals to 1. Okay, so you cannot separate once you know that suppose one of the is not converged. Okay, you cannot use this result. Okay, right. Now you can have another example is, you have, this is going to be let's say another example what we can take is let's say 3n plus 2 divided by n plus 1. Now see, this going to be, I can write this 2 as plus 3 minus 1. So 3 times n plus 1 by n plus 1. So you have 3 minus 1 by n plus 1. Now, since this is a constant sequence, if you look at this as yn, if you look at this as zn, both sequence converges, and the zn converges to 0 and yn converges to 3. So then you can have limit of xn is equals to 3 minus 0, that is 3. Right. So you can use this algebra of limits here as well. Okay? Right. So these are the results which we are going to see in the next class. That if you take a sequence which is convergent, and if each term is non-negative, then its limit is also going to be non-negative. Okay, so limit of a sequence of non-negative real number is also non-negative. Okay, then you have the next result is you can. So once you have two sequences, both are convergent, and if you are able to establish this relation, that comparison relation, you can say xn is less than equals to yn. For example, 1 by n plus a is less than equals to 1 by n. So this is your xn, this is your yn. So for all n, then limit of xn is less than equals to limit of yn. This is going to be a corollary of this. This you can use here. Okay. And the third thing is, if the sequence convergent, means it is bounded, and if xn is lies between a to b, this interval, then this limit also, its limit also lies between interval a to b. Okay, so these three results we are going to look at in the next session. Okay, thank you. And if you have any questions, you can ask.
Sir, I was a doubt regarding that k epsilon naught plus 1, k epsilon naught plus 2 would be near the point. Then would they be in the bounded area or outside the bounded area?
Bounded area. You have this k epsilon is sitting on the you can say right of the very right of the number what you are deciding here. So suppose this is the number 1 by epsilon minus 1 is somewhere on the real line. You are just taking the next
integer. K epsilon naught plus 1, k epsilon naught plus 2, k epsilon naught plus 2. So we have choose that n greater than k epsilon naught.
Yeah.
So would it be inside the bounded area?
Inside the bounded. See, k epsilon are the natural numbers. This is infinite sequence. Suppose k epsilon is starting with 1 lakh. K epsilon is equals to 1 lakh or 100, suppose. So the next number is 100, 100, 200, 300, 400, so on. They are the numbers. That's not ending series. What is remaining bounded in means xn, the sequence, that sequence xn, the member of this this values. Okay, that they are remaining closer to x.
Okay.
Okay.
Yeah.
K epsilon is not bounded. K epsilon is going infinite.
Okay, got it.